Our speaker today is David Strohbar with Beville Engineering, and also he's with the Center for Operator Performance. After beginning his career at 3 Mile Island after the incident there, David Strohbar founded Beville Engineering in 1984. Beville conducts human factor engineering analysis of process plant modernizations, operator workload, and alarm display systems for companies such as BP, Phillips, Chevron, Shell, and others. He has evaluated operator workloads on over 1,000 units at over 80 different sites for over 40 companies. In addition, he's participated in over 150 alarm rationalizations. My heart goes out to you on that one. Mr. Strohbar was one of the founders of the Center for Operating Performance. That's a collaboration of operating companies, DCS suppliers, and academia, which research human factor issues in process control. He's the author of Human Factors is Process Plant Operations, Momentum, and that's with Momentum Press, and was the Rationalization Clause Coordinator for ISA 18.2. By the way, there's some people that have joined from 18.2 in this presentation. Alarm management for the process industries. Mr. Strohbar has a degree in human factors engineering and is a registered professional engineer in the state of Ohio. With that, David, I will welcome, and we'd like to hear what you got to say.
Okay, well, thank you, Dave. I'm hoping that most of the people here were able to attend last Friday's meeting where Dr. Camille Perez gave an excellent presentation on human factors, some of the key elements associated with it. And she started by talking about how she got involved in this particular area, and she cited the explosion at the Phillips chemical complex in Pasadena, and that's a picture here that she used where you can see individuals watching the fire from some distance away. I personally was at Shell at Deer Park and felt that blast when it occurred. I had to talk to engineers out of not quitting that particular day, and this was in the era of answering machines, and so I called my wife in Ohio and said I'm getting an error message. No, I don't want to debug. And I had to leave the message that said, whatever you see on the news, I'm okay. So I have a same connection with that particular event. Take you a little farther back, though, and a sort of connection between my career in nuclear power and my career in oil and chemical processing. I was asked by Amoco at the time to talk about the accident at 3 Mile Island. And so this was to a group of Amoco safety professionals. And so I was taking them through the basic issues associated with the accident. So what you're seeing here is a rather simplified version of a pressurized water reactor. So I've got the nuclear core generating a lot of heat. I've got water that's flowing through the core, going through a once-through steam generator. Heat is being removed, boiler feed water is going in, superheated steam is coming out, and the cooled water goes back through the core. And so this, what they call the primary coolant system, is to remain liquid at all time. Since it's running at 620 degrees Fahrenheit, they have to maintain about 2100 psig to ensure that it stays liquid. And that's done through a pressurizer here on the top of the system. And that keeps the pressure on. The pressurizer is also instructed to the operators. They were told that was also an indication of the inventory in their primary coolant system. So that pressurizer level was increasing, that meant they had more coolant. Pressurizer level was decreasing, that they had less coolant in their primary system. It's a closed loop system. So the particular event that occurred actually started with a maintenance activity around a condensate polisher that resulted in a trip of the boiler feed water pumps. So I no longer have heat removal in the steam generator. Temperatures increase, and the reactor trips. And so far, all the safety systems are functioning as designed. And so the reactor trips. And what you typically see, the relationship in the reactor on pressure and temperature, this blue dot is sort of the normal operating range. So this is where you would expect the pressure and temperature to be. A standard or typical trip, what should happen is you should see a slight pressure decrease as the system compresses with the lack of heat, and it eventually recovers and ends up cooler, but about the same pressure as the pressurizer takes control. So that's the characteristic response that you would like to have. On the evening, the night, the 3 Mile Island accident, when that reactor tripped, what happened was this pressurizer, the pilot-operated relief valve opened up to relieve some pressure, and it failed to reseat. And so that was the initiating event on the accident. Was that relief valve was essentially stuck open. And so the pressure begins to decrease. So if you look here at the pressure temperature plot, so it follows the initial pressure decrease, but then the pressure continues to go down. At 1,600 pounds pressure, there is a safety system that starts high pressure injection pumps to put coolant into the system. And those pumps worked as designed. So at 1,600 pounds, the high pressure injection pumps kick in. They start putting more coolant into the system to keep the reactor cold. Shortly after the automatic system initiated, the operators overrode it and shut it down. So they shut down the high pressure injection pumps. And so at that point, you now have really what would be considered the sort of the first air, if you will, that eventually led to the destruction of this reactor core in this unit and the destruction of the nuclear power industry in the United States. And I'm sure you're saying, well, why would that occur? Why would they do something like that? Well, part of the problem was they're seeing this pressure drop that's occurring, and that does happen if I've got a leak in the system. But also what was occurring is this pressurizer level was increasing because I have a leak out the top of the pressurizer. And so this pressurizer level is going up. Remember I told you that was, they had been taught that was indication of the inventory in their primary coolant system. So they saw that pressurizer level increase. They're thinking, oh, I have too much coolant. Too much coolant would also cause a pressure drop because you're going to be compressing the primary coolant system. So their assessment of the situation was they were in an overcooling event when in fact they were in a loss of cooling event. So they overrode the safety system and shut down what could have potentially saved the reactor core. And you say, well, how do you make a mistake like that? Well, part of it had to do with how you're presenting information to the individual. So this pressurizer level or pressurizer control valve, a pilot-operated relief valve, there's a single indication on the panel. So this is what the operator would have seen. It was a little backlit light, PORV, pilot-operated relief valve. When the demand for that valve to go open was present, in other words, the pressure was high enough for that valve to go open, that light would turn green. When the pressure had been reduced and that valve no longer needed to be open, the light would go out. And what was happening is the operators were interpreting that light to be actual valve position indication or valve status. And in fact, all it was demand indication. It was only asking what the system wanted the valve to do, not what the valve was actually doing. So when they see the pressurizer level increase, they look at their valve and they see that the valve is dark. So they know that they're thinking, well, it's not leaking out the top of the pressurizer because my valve's closed. So I must be in this overcooling event. So let's bypass the safety system to prevent from making matters worse. And I share this story with you because when I went through this at Amoco, I took a significant verbal abuse afterwards because they were saying, well, that could never happen in our plants. We would never allow a safety system to be bypassed. This was clearly a case where the nuclear industry had some significant problems. Well, cut to maybe a year or so later, I actually happened to be at the Amoco refinery in Texas City, and I'm talking to an operator on what was then their acid plant, since been shut down. And we're going through a particular upset, and the operator said, well, one of the first things we do is we bypass the shutdown system. And he showed me where you would do that. There was some controls on the wall, and it was under a locked plexiglass panel. And that's where you could bypass the shutdown system. And I said, oh, well, so you need to get a key in order to open that panel to bypass the shutdown system. And they said, well, we could do that, or what we've learned is we can just pull the hinge out of that panel and access it that way. So we don't really need the key, and we don't ask for the key. We just pull that metal hinge out, we open the panel, and we bypass the shutdown system. So the notion that operators don't bypass safety shutdown systems, I found out very quickly, was not a unique feature in the nuclear power industry, but you see it at a variety of locations. So Dr. Perez was going through and talking about some of the origin of human factors and where it came from. World War II was one of the key places where that was happening. She talked about Alphonse Chapanis, and he was looking into why there were gear-up landings, and it had to do with the controls for the flaps and the landing gear were very similar, and the pilots were, instead of lowering the landing gear, they were adjusting the flaps, and so you were having these gear-up landings. So again, another case of, quote, operator error. And as she talked about, she called it designer error. I'm used to the expression design-induced error, because the design of the system is what prompts that. Now, some people might be thinking, oh, well, that's, 80 years ago, World War II. Technology certainly has advanced. We certainly couldn't make those same sort of mistakes today in terms of what's happening. But it turns out that perhaps the designers of systems are still human, and they still make various mistakes and errors. I was at a chemical plant, and I'm out in the unit with an operator, and we're watching as the maintenance personnel are coming up to work on their safety shutdown system cabinet that's out in the unit. And there's two cabinets out in the unit. Both of them had these large indicator lights on them. One of the cabinets, bright green light, was lit up and on. And on a different cabinet, a bright red light was lit up and on. And so I'm used to their control room, because that's where I'm typically at. To their console operators, red means stopped, it means warning, it meant closed. So if a pump had been stopped, it would show red. Valve was closed, it would show red. If a pump was running, it would be green. Valves open, it would be green. That's a color code that typically isn't used as much today, but you still see it around. However, out in the units there, those particular safety shutdown panels, they were using the electrical industry convention, where green meant de-energized and safe to work on, and red meant energized, not safe to work on. So here I had a mismatch between what the maintenance techs in the field were doing and what the console operator in the control room was seeing. And of course, they had to coordinate their actions. That day, nothing bad happened there. I don't know if anything ever did, but those are the sort of situations that if you were to go in and try to quantify, potential for operator error, they would rank very highly, because now I have a mismatch between the indications that the operators and maintenance techs in the field are seeing and what the console operator is seeing on the panel, and what they're trying to deal with. So while yes, the human factors started in World War II, we're still seeing the same sort of events that are occurring, that were there present. In this case, mismatch controls, mismatch indications that are happening today in almost any plant that we go to. So Dr. Perez broke down the area of human factors into 3 different categories, and this is a little bit, so I want to talk a little bit about that. So she talked about information processing, where one of the key things that we find errors occurring in is in around how people are processing information. So what I'm showing you here, this is a very simple operator in the loop feedback control mechanism. So I have some sort of process with some output that's occurring. That output is compared to a reference where, where am I at? Where do I think I want to be? And if they're significantly different, an error value, deviation is created. And if it's significant enough, hopefully the operator will take action to bring the process back in alignment to zero it out. So what has to happen for the operator to do that? Well, there's really 3 different steps involved when this is occurring. First, I have to detect that there's an error. I have to know that something's wrong. I have to identify, well, what is it? What is it that has occurred? And then I have to take action associated with that particular step. I have to compensate for it. Where you find a lot of the major accidents that involve what we would call human error or design-induced error really deal with these first 2, the detection and identification steps associated with it. So failure to detect, that is a key item where they don't even realize that anything's wrong. And so you can find it a couple different reasons. I was at an olefin plant one time, and their alarm rate was coming in so fast that the operators essentially had ignored it. There was no point in looking at the alarms. They were coming in constantly. Most of them didn't mean anything. And so the operators really weren't using the alarm system at all. The area manager of that particular unit was asking me about it, and I said, well, I can guarantee you with 100% that the operator is going to miss an alarm, that there is going to be an alarm that you want them to take action on that they're going to not see, and they're not going to take the appropriate action. I said, the problem is I can't tell you which alarm it is. I don't know which one they're going to miss, but I can guarantee you that, with 100%, they're going to miss some alarm that's in there. You hope it's a, alarm that has low impact on the plant, but it could quite likely be a more serious alarm that's happening. So you can have the problem where I'm having so many alarms, I don't even notice that there's a problem that's occurring. I can have issues where I fail to detect it simply because it gets lost in the noise of the system. I was at a plant. This was a Canadian refinery, January 1st, so the middle of winter. The operator had an alarm come in related to low level in their treated water tank. And for a variety of reasons, they failed to take action when that alarm came in, and it stayed on the alarm panel for 8 hours. So they went 8 hours with no treated water coming into their treated water tank, and 8 hours later they tripped all the boilers on loss of boiler feed water. How do you go 8 hours with an alarm and not take action on it? Well, it was one of many alarms. They had about 20 alarms on their alarm summary screen. This treated water tank level alarm was just one of many. And so it just blended into the background. And again, the operator, failed to notice it. Interviews with the operators afterwards, you said, I know I was sitting there, I was logged in. I see that the alarm came in, but, he said, as God is my witness, I do not recall ever getting a low treated water tank alarm. So he didn't know anything was wrong. And as a result, nothing was done. And so the operator didn't take action. That was a treated water tank alarm. But obviously, there's a whole variety of alarms that it could be. It could have been a fault with their safety shutdown system or some other, H2S alarm, something that was more significant that would have required serious attention. So failure to detect, common problem that we see in a lot of different events within the refining and chemical processing industry. One of the major ones is the misidentification. So the next, you're hoping the operator, assuming that they've detected that something's wrong. Yes, I know I've got a problem. Now I'm going to, I need to identify what that problem is. And so the identification of, well, what is it that we need to do, what needs to happen becomes critical. Well, we've already talked about one of those cases, the 3 Mile Island accident. How did they bypass their safety system? Why did they bypass their safety system? Well, they misidentified the problem. They thought they were in an overcooling event when in fact they were in a loss of cooling event. So failure to generate the correct identification. But it isn't unique to the nuclear industry. And in fact, we saw this at a particular refinery in a somewhat ironic situation. At this particular refinery, they had put in a fault-tolerant safety shutdown system on the fired heaters for their crude unit. And with that, they were suspicious of their alarm system. So they said, well, we don't want to have the safety shutdown system on the heater alarms, and we don't want those mixed in with our process alarms. So we're going to install its own dedicated hardwired annunciator panel so that none of those SIS alarms are going to get lost with the other alarms. Well, they had an event. The plant is going through an upset. So eventually the conditions for trip are met and the heater trips. Well, during all of this, a lot of alarms are going off, very chaotic position. So if you were to look at that annunciator panel, in order to facilitate the processing of the information, they had color-coded the tiles on that panel. So white tiles indicated that had to do with some sort of fault within the SIS communication issues or something like that. There were red tiles on there that indicated a pre-trip condition. So if you met, you were nearing a trip, but you hadn't reached it, you would get a red tile alarm. And if the condition continued and you actually tripped, then there were green tiles that lit up to indicate that you had tripped. Well, at this particular plant, they're rocking and rolling, the heater trips. Well, the operator looks at that panel, and of course, what do they focus on? Well, they focus on the pre-trip. They focus on the red alarms and fail to notice or factor in the green alarms that were there. So this was their best console operator. He sees this. He thinks he's going to recover from it, and so he says, I want to have the field operator bypass the chop valve on the fuel gas system to that heater. I don't want to lose the heater. And so their best head operator was standing behind him, and he says, I agree with you. And the shift supervisor behind the head operator said, I concur. So you had 3 extremely experienced and qualified operators that all thought it was a good idea to bypass the chop valve and essentially put fuel gas into a hot heater that had no flames. Needless to say, they did that. The fuel gas eventually hit a hot spot and exploded. Fortunately, no one was hurt, but the field operator was blown off the heater deck when it happened. But if you said, well, how does that happen? Well, they misdiagnosed. They had misidentification of what the event was. And despite all their efforts to ensure that their safety system did what you wanted it to do, it really didn't have the desired effect. So information processing, that's one of the key areas, and I urge you to get Camille's presentation, and she goes into some more of the details of what human factors we're looking for from the information processing standpoint. But certainly it's an area where it is there have been causes of incidents over the years related to this inability to either detect or identify or finally compensate for a particular problem.
Hey, David.
Yeah.
I want to give you a chance to catch your breath here. I got to investigate a heater that had blown up, and it's around misidentification. It was the lights on the furnace pilots were facing the east, and there were 10 burners, but the 5 burners that were facing the east, the sun was hitting him just right that morning, and he had a flame out, and he didn't realize it. He did because he looked at the indicator lights in the shade, and they were off, but he looked at the indicator lights in the sun, and they were on. And so the operator, he got confused, and there was this moment of confusion, and he ended up hitting the igniter and causing the heater to explode. Luckily, there weren't any injuries there, but sometimes it's maybe not how it's the environment around us that cause us to misidentify, right?
Well, and that's where somebody say, oh, it was a case of operator error. We would say, no, that was design-induced error, because the designer should understand the environment that it's being used in and realize, well, if this is in the direct sun, then I need to provide some sort of shading, or I need to use some other indication to provide that sort of indication. So the operator, and this is what we would say, the operator was being set up to fail, and he did fail, but it was because whoever designed the system really didn't think about, well, how are they going to be using this? Where's it being used at? And doing the correct design, because as you obviously found out that this particular design doesn't work in bright sunlight. And if it was night, would he have made the same mistake? Probably not. But they didn't design for all the operating conditions.
Right.
So that's the you see it all the time. Dr. Perez, she talked about the organization, which is really the sort of environment that they're functioning in. I'll bring in one last issue around from the nuclear power industry and from an organizational standpoint. This was early on. I normally didn't have to write purchase orders or requisition material, but I eventually was doing some alarm tiles for the control rooms at 3 Mile Island Unit 1. And I was filling out the purchase order, and this old project engineer comes up to me and he says, oh, hey, write on there 49 CFR 10 does not apply. And I said, well, what is that, and why am I writing that on there? And he says, don't worry about what it is. He says, but if you don't write that on there, then your purchase order is going to go to quality assurance, and you're never going to see your alarm tiles. And so they had created a system that was so complex that people had learned to develop workarounds in order to actually try to get their job done. And so in this case, it was probably not an issue, but we're seeing that more and more, where if you're going to thwart human behavior, humans are very good at finding ways around it. And so from an organizational standpoint, you not just have to look at, well, what are we trying to achieve, But what are we likely going to do as a result of that? One of the issues that the Center for Operator Performance tackled a number of years back had to do with fatigue management. And this was when the guidelines were coming out in terms of continuous days on the job. And so the Center for Operator Performance underdid some data mining at four different refineries across the U.S. And so they were looking at what the percentage or probability of operator error was based on continuous days on the job. So this chart that you're seeing here, what you have is, this is the error probability for each day on the job. And so as you see, days 1 through 8, you have a fairly low and consistent error probability. So the probability of a person making a mistake on days 1 through 8 of working, essentially the same, doesn't really matter. However, between days 8 and 9, that probability doubles. It doubles again between 9 and 10. And at 11 days, continuous days on the job, you get a 6-fold increase in the probability of operator error or human error. So the management's decisions on how long can an individual work a job continuously is going to have an impact on what is the probability of an error. If I'm having to manipulate some sort of system, some sort of safety system, either maintain it or operate it, and I'm doing it on my first 8 days on the job, well, chances are I'm probably not going to make a mistake. But as I start increasing it, that probability goes up dramatically. People have asked, they said, well, what about, past day 11? The problem was we really didn't have enough data in order to be able to make any judgments on that. So, that would be a question that you might want to have. So organization comes into play, wiring up safety valves. That's something when I'm out with operators in the unit. Again, you don't see it as much anymore, but you certainly see places where, the wires are there near the safety valves so that should they trip, they are not going to close because somebody's wired them up, that they can't happen. I was with an operator, it wasn't a safety valve, but it was a spring-loaded valve. So again, we're trying to make sure that this valve wasn't open and the operator would walk away. We were out on the unit, we go to that valve and the operator opens the valve up, there's a wire, puts the wire on it so it stays in the open position. The irony of this particular one was this operator, we had just come from the shift change meeting, the very beginning of the meeting, where they had emphasized, the safety and be safe out there and let's do things the right way. And this was for a company that routinely gets accolades for their safety culture. And 10 minutes after that meeting, we walk out, he takes that spring-loaded valve and he wires it up. And so again, we would attribute that to sort of the cultural issue that they're operating in. He is bypassing a safety system, and somehow the organization has not imparted on them the need that, that's not how we do this. This is not the way that things are supposed to be done. We've seen it in others in terms of when we're talking about alarms and alarm response. Plant I was doing early on as part of alarm rationalization, you document what action is the operator to take when a particular alarm comes in. And so we got to this one alarm and I said, okay, what do you do when this alarm comes in? And they said, well, the first thing we do is to bypass the safety shutdown system. And I said, well, I'm a little reluctant to put that in as the official response for what you're supposed to do on this alarm. And they said, but that's what we do. That's why the keys are in the safety shutdown bypass switches on the control panel. This was, they were converting from pneumatic to distributed control. We keep the keys in the safety shutdown system so that when we get events like this, alarms like this, we can immediately bypass the SIS. And so I was able to convince them not to document that they should bypass the safety system, but they all assured me that is exactly what they did. Now, those keys are sitting in those locks, so certainly everybody in at least middle management knew what was going on and how they were doing it, and yet the organization allowed it to continue. So the organization in which the behaviors is occurring, again, strong influencer on, are you going to have a situation of, quote, operator error, or the operator taking improper intervention on the system? One of the final items that Camille worked on, I got to tell you, Camille is one of the best in terms of being able to, looking at procedures and knowing what needs to be done. And so what we find, we look at procedures and how operators actually use them. What you end up with is some real problems in that one of the things, particularly for emergency procedures, is the procedures tend to be based upon a particular unit. So this diagram here that you're seeing is not uncommon. So I may have 3 different units under a single operator's span of control. So he's controlling these 3 different units. Unit A may have only a single operator that works it, but unit B and C are both handled by one operator. So this operator has 2 units that are involved. So when they have a problem or they have an issue and the event occurs, and I'm actually supposed to use the procedures, then I run into problems. So I was actually with a console operator in this scenario, and we were going through a power dip event, and he pulls out 3 3-inch ring binders, one for the power loss on each of these units. He has them sitting in front of him. And of course, I asked the question, I said, so how does this work? Do you do all the steps on unit A and then go to B and then C, or do you do step 1 on A, step 1 on B, step 1 on C? And he just kind of smiled at me and shrugged his shoulders and said, well, your guess is as good as mine. I'm not sure what order I'm supposed to be doing this in. So you have a case where the procedures aren't really reflecting the job. They're taking a hardware-based approach to it. I'm going to look at the hardware, not what the person is expected to do. So you end up with this situation where you have this, I need to have multiple procedures. I have to use more than one, and then it's up to the individual, it's up to the operator to integrate them together. So if this console operator had waited too long to take the tasks on unit B because they were spending more time on unit A, whose fault is that? Is that the operator's fault? Well, gee, you didn't get to those tasks in the procedure. It says to do them, and you didn't get to it, so you made a mistake. I cringed when the initial findings from the BP Texas City incident came out, and they talked about that it was a procedural, the operators didn't follow procedures. And one of the comments I made is I said, well, there's an assumption there that the procedures are followable, that I can actually use the procedures. And I would argue that in many cases, you can't actually use the procedures, that they aren't going to do for you what you want them to do. So you've got this case, I've got these multiple procedures. A lot of times within those procedures themselves, I've had it one where there were 8 pages of steps for what the console operator was to do before you got to any steps that the field operator was supposed to do. So because it's written based upon the unit, not based upon the job or the position that the individual has. The Center for Operator Performance found some real problems in terms of the content of the procedures. That it turns out the content of the procedures is not particularly unique, and so this has been repeated in a couple of different situations. But we looked at one set of emergency procedures for an area of a refinery, and there were 40 pages of emergency procedures covering all the different events. But what we found is that in most of those procedures, there's a large repetition of basic tasks that they had to perform. So if you look at this chart to your right, what you're seeing is the number of different unique steps that are contained in those 40 procedures. So there's 127 steps in 23 different chunks or modules that were made up those 40 pages of procedures. If I were to print this out for you, it was 4 pages. So 40 pages of procedures were created from 4 pages of content. And so there's a lot of repetition in the procedures. What that does is it increases the volume. You know, I now have to have 40 pages, and when I have to do annual updates and revisions, now I have to revise 40 pages. It looks like a daunting task. Well, the reality is there's only 40 pages there's only 4 pages of unique content. The rest of it is just how I arrange that content across the different procedures. And it also makes it more to learn. There's a lot of plants that require their operators to learn the emergency procedures. And how do they do that? Well, they do it procedure at a time. And yet, if you were to look at it, there's really only 23 tasks, if you will, that they need to learn. If I learn those 23 tasks, then I've learned all the tasks that are in all the emergency procedures. Again, they're just reoriented. Some have more tasks, some have less. But the way in which we're presenting the information is making that far more difficult than it need be. So those are some of the key areas. So again, I urge you to watch Camille's presentation if you weren't able to catch it. But the human factor, operator error, it was present in World War II. We see it today, can have catastrophic consequences if operators make the wrong diagnosis, or they fail to detect a problem in which it's necessary for them to intervene. One organization that's trying to help this out a little bit is the Center for Operator Performance. I'll give a little plug for them. These are the member companies of the what we call the COP. So BP, Chevron, and its affiliate Chevron Phillips, and the various Koch industries of Flint Hills Resources, Georgia Pacific, and Vista, Nova Chemicals and their European collaboration with Borealis, Holly Frontier on the refining front, along with Citgo on the refining front. Emerson and Yokogawa are DCS suppliers who participate in a number of the studies. And our most recent addition, BASF, with a chemical perspective. And we provide support for the center. But the group here is designed to research how do we improve operator performance. If you happen to be a member of one of those companies, you can have access to the members only website. You can simply go to the website and request a membership, or you can go to Beville.com, our website, and we can sign you up for it. But there is both a public site with some information that anybody can use, but then there's a member-only site where you can have access to all the research, like that fatigue data that I showed you previously. That's in there. If you want some more information, Center for Operator Performance, the public site is operatorperformance.org. If you are a member, you can go to operatorperformance.net, and at operatorperformance.net, you can have access to all the research that the COP has done from its very inception. Beville Engineering, we have some archives, some newsletters, some information that you might find interesting. Plug the book, Human Factors and Process Plant Operation. You can get that on Amazon. If you get the electronic version, it's in color. If you get the print-in version, it's in black and white. That wasn't my decision, but that was Momentum Press's idea. So the electronic version is a little bit better from that standpoint. I will recommend a book to you. It's called Drift into Failure by Sidney Decker. Dr. Perez talked about some of Decker's research. I found this book to be just very eye-opening, particularly from the safety system standpoint, because he talks about how we try our best to prevent a number of accidents through various interventions and safety measures, and how oftentimes we unwittingly drift from those and into a particular failure mode. So with that, appreciate your time and attention. And so I guess, Dave, if there's any questions, be happy to take those.
There are a couple of statements that maybe you could respond to. One is from Mr. Rique, and that's on USA is clearly world leader for analysis of human in the loop with the MIT STPA methodology. This methodology would be at the heart of safety in the next IEC 61508 daughter standard, IEC 63187. And I'm sorry that we don't have a mic for this person. Do you have any comment to that?
Well, I mean, there's some great tools that are out there. So either some that exist at MIT. Australia is actually doing a very nice job for their size in analyzing operator performance. There are simulation models to be used. Probably in many cases, what's lacking is some good data for benchmarking the models. You know, what is the error probability actually associated with? And just as you found with the some of the procedure comments that Dr. Perez had brought forth, what we find is that oftentimes we will do research that produces data that is counter to what would be considered popular opinion or what we would call folk psychology. So there's a lot of techniques out there. I'm assuming they're recommending the MIT. Very good. And there's a variety of applications that can potentially be brought to bear. And that's part of the Center for Operator Performance. We're not there to develop the technique. We're there to find out how do we apply it to our particular industry.
Yeah, the Australia, were you talking about the IChemE? I just heard a presentation from the lead of the IChemE, for example. Was that your example?
Well, IChemE has done a nice job. Actually, there's just, if you look at, so there's probably the trade organization for human factors is the Human Factors in Ergonomics Society, hfes.org. is their website. But if you look at most of the papers being published in the human factors community, there is a large number from Australia, and Sidney Decker is Australian. So they're doing a lot of cutting edge research in that particular area, but IChemE is doing some good stuff as well.
Okay, good. This one's from Eric Martinez, just making a statement that it's important to consider some accidents that could be prevented by better design. I think that was kind of during your design discussion, and he was just making a comment about that.
Well, and I know there's a tendency, when a lot of people say, oh, well, you never allow for the person making a mistake. And it's always some sort of design issue. You could have designed the system better, you could have trained them better, and to a certain extent that's true. But at the same time, there are cases where there is just random error. And now some of the numbers that are being used are way too high. So if you look at a person manipulating like 100 switches, you would expect a maximum error rate of about 1%. So that would be what you would typically see. So that's random error rate. So about 1 out of 100 in a repetitive task, you're going to find a mistake being made. But it does happen. So it can be there, but more often than not, like your heater example, there was confounding issues associated with it. The person just didn't go up and make a random mistake. They were confused.
Yeah. There's a couple of slides following this that I think could add to some of the questions, but a question I'd like to ask you that's in the slides coming up is, someone, they go out and they party all night and they've got this hangover deluxe, and he's an operator. They come to work and they make a mistake because their head is just not in the game anymore. How do you classify that?
Well, one of the issues, so this has come up in some other industries, is, the nuclear industry, they were evaluating this. I don't know whether they implemented it, but they have a fitness for duty test. So when you come in that morning, you're going to do, so nowadays, you have to get your temperature taken for COVID-19. You're going to have to do this fitness for duty test and make sure that, yeah, you're capable of doing it. People are going to make random mistakes. So that person's going to make a mistake. The question then would be, you should have enough, layers of protection, if you will, that one mistake does not result in some sort of catastrophic event. Because people are going to make mistakes. And the question is, if they make that mistake, is there opportunities for them to catch the mistake or for somebody else to catch the mistake and prevent it from happening? So we'd like to minimize operator error, but it is going to happen. And so then the question is, have you built in a system that's tolerant to operator error? And that's one of the fears in some of the areas regarding the plants today, that we're making them too brittle, that they aren't flexible enough to tolerate error. So one person making one mistake, and I have some sort of catastrophic consequence because the systems have become so tightly interconnected and so brittle that that one error propagates very quickly.
Yeah, I got a few questions coming in, but the follow-up question I just gave you. So if the organization does not have a fitness for duty test, would that be considered systematic? They don't have a system in place to keep the operator within the parameters or failure rate of a operator that's attentive.
So so if they don't have a fitness for duty test, then you would start looking at the organization. So this is where Camille would say, did anybody else notice that? Like, yeah, the whole crew was like, whoo, boy, it's just not his day. And if so, if you all notice that, why wasn't he relieved? Why wasn't he taken off? So from a military standpoint, they would say, well, you're not going to do this because you're not capable of doing this. I will share an anecdote. We were at a plant doing a survey, and I was told by a friend of mine there that during our survey, they made sure the operator who had early onset Alzheimer's was not working. And I said, you have an operator with Alzheimer's? And they said, yeah, he normally works the panel, works the console. And I said, you're kidding, you had him working the console? And they said, well, we can't let him out in the unit or he'd never find his way back. So he would sit at the console, and then the head operator would sit there and essentially cover for him. So they were trying to do a good thing. They were trying to cover him until he had enough years for retirement. But, clearly you had somebody that now, from a crew standpoint, your crew is not at its full contingent because one of the members just really can't function or perform their job.
Yeah. Somebody was, I guess, typing while you were was matching you on fatigue management. They said that's part of what's called FMP, Fatigue Management Plan, Fitness for Duty. So somebody else was just trying to answer with you there. And let's see. Then there's another one from Japan Shaw. And any experience/data for procedures with simulator high fidelity, low fidelity? I guess trying to understand what the value is there, or the risk of human error using high fidelity or low fidelity.
Well, we've got a couple different. So the COP just did a project using high fidelity simulators looking at operator performance with different levels of alarm management and different levels of automation to understand how did the plant performance, not just how did the operator, if I do certain things, I can say, oh, they had fewer alarms or, but actually look at the plant and how it performed. So the whole system, the operator and the system. And so we ran a very interesting test, got some very interesting results using that high fidelity simulator. One of the project that we're looking to undertake right now is skill degradation with advanced process control. So one of the things in the industry that as we've put in these advanced control systems, there's been a definite feeling that operator skill has gone down because they're not intervening in the process as much, and so their ability to react has decreased. And so one of the thoughts was, well, can we use simulation to augment their skill level? So we've got a project right now just first trying to quantify, does advanced process control result in skill degradation? And if that answer is yes, then obviously the next question is, okay, how do we get it back up? And do we need high fidelity simulation, or is low fidelity simulation sufficient? Or can we just do some sort of scenario based training? So yeah, all true and all on the COP's plate of what they're trying to do.
So the answer is working on that.
Working on that, yes.
Let's see. This is back to the same person that asked that question. Japan Shah is one of the recommendations within our organization is that any IPL alarm requires well-documented procedures and all operators to be trained and validated by senior operators. So just more around, hey, this is what we do with, I guess, critical alarms or IPL alarms.
Well, and this, the industry's gotten much better, and the key thing here is, will they see the IPL alarm when it comes in? If they don't do it correctly and it becomes a cry wolf alarm, they'll ignore it because, well, I've seen that 10 times and it's nothing. And, so, just like all good alarm design, you need to have an action associated with it, and it can't get lost in the flood of alarms that are being presented. So there's a lot of, we're certainly getting a lot better with that. But that's, again, its very nature, and why it's so important is, of course, because that is, your last or only layer before something bad's going to happen.
Yeah, just a couple of more comments coming in, but just follow on that is I did an audit at a refinery, and I dinged them because they had identified their critical alarms, but they didn't know what the ones alarms were that they claimed. And I dinged them because, hey, you need to know which ones you claimed, because they were the most important alarms, and you claimed it to keep something bad from happening, as opposed to your other critical alarms. And I got a lot of heat over that, and but I thought it's important that you need to at least know, documented somewhere, hey, these are you claimed these. Any comment on that?
Well, and you need to see how it fits into the entire system. So, there is a time element associated with, priority. So how long do I have to respond to this alarm? Usually, if it's an IPO, it's pretty fast. So, it's going to be the highest priority that's in there. But then the question, well, what else do I have in that particular system? So I was at one refinery, this is a number of years ago, but they had a distributed control system, but they also had hardwired annunciators because they didn't trust the alarm system. And for one fluid catalytic cracking unit, they had 12 annunciator panels that were wrapped around the consoles, and every tile on those 12 panels was red. And so I said, why all the red tiles? And they said, well, those are all important alarms. And of course, they failed to see the irony that, well, if they're all important, then none of them are any more important. So, you can look at these IPLs and they may be treating it well, but you also have to look at it as part of the bigger picture. How are they going to be able to detect that when a lot of other things are going on, or if that IPL is an emergency priority, but I have 100 other emergency priorities, am I going to see it? And obviously you want to make sure that IPL stands out from the others.
Yeah, getting a few questions on alarms and how it relates to safety systems is we rely on operators to do the right thing 9 out of 10 times to keep our safety systems from having demands on them. So I guess that's why we're getting alarm questions in here. Another one is a method that is often recommended is the HART method for evaluating human error probability. How relevant is that today? Are you familiar with that?
I'm familiar with the HART technique and the new reg THRP technique for human error rate prediction, and both of them, there's no problem with it, but they both rely heavily on expert judgment as to what the error rate probability would be, and so that's where we need data. We don't know how often somebody makes a mistake because we don't really capture. We neither capture how often do they perform that task, nor how often is a mistake made that proves to be a non-issue. So I was with a field operator and he was doing a lineup, and he lined up a silo to the wrong one. He wanted to go to silo A and he did the lineup incorrectly and he went to silo B. And as and he was moving off spec material. Well, he got lucky because silo B happened to be empty, so he didn't contaminate any product with his lineup error that he made, and so he was able to cover it. Nobody knew that he made that mistake, but he did make an error, and so we don't have enough data to understand how often are they going to make a mistake, because maybe we could figure out how often they did the lineup, but we're not capturing how often an error occurs. And of course, he didn't even think of it in those terms, but I saw it and said, wow, he's made a mistake. This could have cost the company, thousands of dollars because of this particular mistake. You just got lucky, and you happened to your mistake. You lined it up to a silo that it was a non-issue for.
So, Mr. Kirkwood, I guess it's relevant today if you have somebody that is understands what it is and how to collect data on it, I think is what I'm hearing from David.
Yeah, and again, it's something that I think the industry as a whole needs to do more of. So again, the techniques are good, but you have to have the right data to plug into them.
I have one more alarm, and then I'm going to switch over to Angela. She's asking about turnaround and some things, and I'd like her to ask those, but let me ask one more here. We normally take one IPL credit for an alarm, but there's many factors about that. Alarm, operator intervention, procedure, alarm action, but how to measure the operator intervention? Do we have any method to give operator, I think he meant figure, not finger. To give operator figure RRF risk reduction factor? Do the critical alarm always considered an RRF of 10? So this is again on alarms, and we're really kind of more focused on safety systems, but you got any comment on that before we move?
Well, again, and that's where I said, you can identify alarm and say, oh, well, this is an IPL and we're going to do it, but it's fitting into an alarm system. So, I gave you that example of the plant where I said, there's a 100% chance you're going to miss an alarm. I just know which one it is. It could be an IPL alarm. So they could have done all their work, up to that point. But if the rest of the system is, likely to cause a mistake, it just gets put into that same basket.
Yes, that refinery did not have a 1 out of 10 chance of failure. They had a higher chance of failure. And so I'm going to switch over to Angela for this next question on fatigue and turnarounds, if she wants to turn on her mic and give that a shot.
Yeah. So Yeah, we've had a lot of discussion about, whenever we start talking about error, it frequently goes to the operator. The scope of our committee on I&E includes a lot of maintenance tasks, and where we heavily we're challenged to very prescribe what an operator's action is to an alarm. Many times our instrumentation and electrical or controls people are entering into troubleshooting mode. So there's not a specific procedure for them to deviate from. There's procedures and there's knowledge and their training, and they're just supposed to figure it out. So I currently have about 70 people on providing turnaround support, and some of those guys have already been working 12-hour days with very short fatigue breaks now for about 6 weeks. And that's the way the job is scheduled. It's the way those particular guys want to work it because they're out of town, so they want as many hours in a week as they can get if they're going to be in a hotel room anyway. So I know there's been a lot of focus on operator error, but what about maintenance errors?
Yeah, that's to you, Mr. Strohbar. I don't know. I was looking at his mic. Whether it was.
Oh, somebody had muted me.
Okay.
So so I would assume the same sort of data on fatigue that we saw with operators, you would see some similar sort of with maintenance personnel. And one of the questions that was raised with the data is it supported the normal operation that 7 days in a row is what you're shooting for, and then you have some time off, but during turnarounds you can go up to 14 days in a row. And so the question is, well, if we're seeing a six-fold increase in error probability with day 11, what happens on day 14? Well, the question is, do you have other systems in place for those, particularly for those later, periods that are going to try to compensate for, you have a higher error rate? So are you doing more checks? Do you have, and that's, again, this is where procedures would come into play. Do you have the appropriate way to ensure that they are performing correctly? And so as fatigue is going to be an issue, then it becomes a matter of, okay, do we have other systems in place, either management systems or we've designed it so it's a non-issue, to try to tamp that down. So certainly your maintenance people here on week 6, their probability of making a mistake is far higher than it was on week 1. And so now, some actions you might have taken week 1, you would say, well, this is superfluous. We don't need to do this. We're not going to make that mistake. Week 6 might be a different story, and that's where you would have to look at what have you put into place as essentially a double check on the system.
Right. Well, okay. So on the double check, I mean, when it comes to operations and double check. CCPS has been very negative on those double checks, actually substantially reducing the error rate because people don't check one another. But I at some point you have to have some process that you're saying, okay, I'm setting this up where, okay, it's not this guy's going to check his own work. It's a QA QC person who's dedicated to checking, and they're only working 40 hours a week and blah, blah, blah. I mean, I'm not sure how I would ever resolve. It needs to be someone super fresh on week 10.
Well, some of that may be a matter of rotating, out of something they're normally used to doing, if they're still qualified for doing the checks. So, variety is going to sort of recharge them because they're not going to get into that routine. You're right, a lot of the double checks are very poorly done. Was at a plant where they had instituted this policy that for lockout tagout, instead of a single operator lock, you had to have 2 operators put locks on, but the operators just went around together and put their locks on. And so now it just took 2 people to do what 1 person could do before. So, it's not just that you do the double check, but how you've created it. But again, the what's happening with the fatigue is, you're going to get these sort of behaviors that they're used to be performing that are inappropriate for whatever the new situation is, and that's what's going to happen. And that's where you see it. That I have some situation where I am applying behavior that normally would work, and it's inappropriate under this circumstance, and I failed to identify that the circumstances have changed. But that's where, if you get somebody where that behavior hasn't become that sort of rote, they're going to see it from a novel standpoint. If you can rotate people around either by crews or by craft, or just a sort of, again, literally fresh eyes on the situation, so that they may spot something that somebody else is going to say, oh yeah, I guess I shouldn't be doing that here, even though it's something we always do.
Another follow-up on that. I have found in managing my staff that I can't ask them to do something and then essentially have them check the information with the data being in the same format. So let's just use something as simple as a timesheet. If they fill out a timesheet and then I ask them to check their timesheet, if they've made an error in it, they're like 100% to approve the error. But if I take that timesheet and instead of running it calendar view, I run it list view, or I change some aspect where it looks different when they print it and look at it, then I find that they are able to identify their mistakes easier. So in this dealing with back checks, I mean, that's anecdotal evidence on my side.
But no, it's absolutely true. And so you're changing the perspective on the problem. And with that, then they're seeing the flaws that they were so accustomed to seeing elsewhere. And so if you can change, so I either change the way I present it or I change the person who's viewing it. But yes, absolutely, that's an excellent technique if you can come up with ways where I'm going to look at it from a different perspective, and the problem's going to pop out. And you're going to say, oh, wow, I'm surprised I didn't see that before. But yeah, we tend to see what we expect to see. And so, if I don't see it in a different way, yeah, I'm going to see that, that same mistake gets carried over time and time again.
So we've got a few more minutes, so I'm going to close this meeting down fairly early, give us a mind break as well as a potty break before 3 o'clock. But a few more questions that have come up. One is from Glenn Merrill. What about the practice for assessing for work-focused or task-focused error where the operator is used to performing the repetitive tasks and ignores external hazards that may arise? Much of that is human factor consideration. I think you just kind of touched on that.
Well, yeah, because you get used to doing something, and one of the key difficulties is for people to understand that this situation is not the same. Something has changed. Something is different about it, and that's a lot of what management of change is about, is understanding that, hey, this is now different, and you need to take a new course of action. And so yeah, that's a key part of the human factors, where I've got some repetitive task that I do day in and day out, is understanding that if the situation has changed, what's going to flag that for the individual. Now, some of it may be organizationally, the beginning of shift meeting, hey, this relief valve is blocked in, and so we have to do this differently now. This isn't the same thing you're used to doing, and you need to be extra careful, take additional cautions, whatever it is. But that recognition that my state has changed is a key part of preventing error.
Thank you. One more question, and then what I'm going to do with the remaining 10 minutes or so is set up for the 3 o'clock meeting. And one is from was it Fresh Eyes that identified the TMIPORV situation? This is from Nick Sands.
Well, so how did the event at 3 Mile Island end? It was the oncoming shift supervisor. So when he came in the morning for relief, they're in the middle of this upset, and he said, well, it sounds like it's, we've got a leak out the pressurizer. And the crew that was on said, no, we checked that. That's not the problem. And he says, well, just close the block valve anyway. I don't care, because there was a block valve on the line that they could close. And they said, well, there's no point in closing it. That's not where it's coming from. He says, well, just close it anyway, because that's what he thought was happening. And sure enough, they closed the valve. And that's when the event ended. The leak stopped at that point. So it was those fresh eyes coming in and hadn't got caught up in the scenario of, well, we think it's an overcooling event, and so we're starting to look for everything that's associated with that. The fresh eyes come in and might say, I think you've misidentified what's going on. And so, that is what it ended the event at 3 Mile Island. But by that time, the damage had been done.
Yeah, Camille had made a couple of comments that I think I want to kind of close down the question and answer here at the end. I think when she's talking about some good, solid investigation. That she was talking about this. I think this means recognizing that something is different, that something operator was repetitive, and that something's different, and it may be that. There's procedures or tools need to be different. The other thing she commented on was, I think having workers become aware, and I'd like to highlight that, become aware of the effects of fatigue may be interesting as well. It's like something to have people be aware. Like, for instance, she didn't write that. I'm making an example here. Is heat stress or heat fatigue, is more training on knowing how to become aware of fatigue, right?
Well, yeah, so that would be potentially one mitigating factor for people to judge themselves. Although I'll tell you, there's a study on truck drivers where they were asking them to rate, tell me at what point you think you're being fatigued. However, they were also measuring physiological measures of fatigue at the same time. And the physiological measures all indicated that fatigue hit before the truck driver said, yes, I'm fatigued. So it helps, but sometimes it can be a little too late. I would recommend there's a variety of books by Dr. Gary Klein, K-L-E-I-N. He talks about what makes an expert. And one of the things that experts or distinguishes expertise is the ability to realize when a situation is not what you think it is, and realize that, hey, this is not the usual thing that I experience, and I need to come up with some new way of approaching the problem.